Hello everybody, this is Dr. Christopher White and welcome back for part 2 of our video series looking at the lab exercise and introduction to geologic cross section. So now we're going to move on to the lab exercise questions. So for question 1, we are going to be looking at this figure right here. Now, this figure you will see has 1, 2, 3, 4, 5 layers of rock, and you can see that 3 of those layers have dip and strike symbols associated with them. 2 layers do not, but if you remember what we discussed earlier, even though these 2 layers do not have dip and strike information, we know they must run parallel to the layers of rock above and below them, because they all have to move as one unit. So how are we going to draw this particular cross section? Well, what I'm going to do is I'm going to come back to PowerPoint and I'm going to paste the image that I copied from the Word document. There it is. Okay. Now, the first thing I'd like you to note is down here in the bottom right, you can see you have this semicircle. This is there to help you orientate your protractor correctly if you decide to use that method. So, all right. So what I'm going to do is I'm going to zoom in. Now, in this instance, we are quite lucky that the line of section runs east-west and our cross section is also orientated east-west. So they're running parallel to each other. So we can drop the boundaries straight down from the map above. So I'm going to do that right now. I'm going to say, right, here is where we have one of our boundaries crossing the line of section. I'm just going to draw that straight down there and okay. And this is going to be the point on our topographic profile where this boundary occurs. Now, the next thing we're going to do is we're going to note the dip angle, which is 25 degrees, and we are going to note the dip direction. So the most important thing is the layer of rock dipping towards A or A prime? That's our key consideration here. And in this case, we can see the dip direction. The smaller part of our dip and strike symbol is pointing towards the right. So it's going to be pointing towards A prime. So that's going to tell us the angle for our layer of rock. So what we're going to do is we are going to draw a horizontal line. This is going to be our layer of rock. Then we're going to go to rotate. We're going to go to more rotation options, and we're going to set that to 25 degrees. Remember, you have the other option, which is you use a protractor, bring your protractor down, you put it horizontally right there, and then you are going to find 25 degrees. So 10, 20, 25 is going to be right there. You are going to make a little mark on the page. So there is 5. I'm going to move your protractor. And then, depending on the technique you're using, you will then either draw your line with a ruler going through that point. Going to come down there, and of course it's going to terminate at the margin of our cross section. The line is going to stop there. So that's if you're using the method where you are printing off this diagram. You are then taking a protractor and a ruler in order to draw the boundary. So that's the first possibility. Or if you decide to use your computer, of course, you've drawn your horizontal line and then you have gone and adjusted the angle, and then you are simply going to extend your line down to the bottom of the cross section there. Okay. Now, the most important thing is you probably worked this out, but I'm just going to make sure you understand that when you look at the dip of our layer of rock, we know the direction of dip from the dip direction on the map. So once again, the dip direction for these 3 dip and strike symbols is pointing towards the right-hand end of the map. That means that the dip for these boundaries is going to be going towards A prime. That's how I know that my layer of rock is dipping in this direction towards A prime rather than dipping towards A. So all you're going to do is you're going to do the same thing for this boundary, this boundary, and this boundary. You're going to project them down, and then you're going to draw the boundary extending underground, and your boundaries are going to terminate at the margins of your cross section. Okay, so that's going to be it for question number 1. So for question number 2, we have a different style of diagram. So in question 2, you will see we have a situation where our geologic map contains just one rock type. It's labeled MK. Now you'll notice that MK has a symbol, and this symbol is a circle with a cross in it, and this denotes horizontal bedding. So the dip of layer MK is 0. It's perfectly horizontal. Now, you're probably thinking to yourself, okay, what am I supposed to do with this? Well, if you look over here, we have an associated stratigraphic column. And you'll notice that at the top is layer MK. However, below MK, there are 2 more layers, DJ and VB. Now, we follow the same basic rule we've used before. We know that these layers must all share the same dip. So even though we only know that MK is horizontal, so it has a dip of 0, we know that DJ and VB must also have the same dip. We also know from the stratigraphic column that even though we can't see them on the map, DJ and VB must be below layer MK. And so on your cross section, what you're going to do is you are going to essentially draw 3 horizontal layers of rock, MK, DJ, and VB. So even though you can't see DJ and VB on the geologic map, you can infer their presence from the stratigraphic column. And so you can draw them as part of your cross section. So you're probably thinking to yourself, okay, I know I'm going to draw these 3 layers, but how thick am I supposed to make them? Now, in this instance, I don't really mind how thick or thin you decide to make each of these 3 layers. Geologists do have techniques that we can use to calculate the true thickness of each layer so we could scale them correctly on a cross section. However, in this instance, we're trying to keep things simple. So all you have to do is draw me 3 horizontal layers and you can choose the thickness that you want to use. Okay, so once you've done that, we're going to be moving on to part 2. And part 2 is going to look at folding, faults, intrusions, and dikes. So for question 1 of part 2, we're going to be looking at this figure here. Now, once again, you can see we have our line of section running east-west from A to A prime, and we can see that our cross section is orientated to match that line of section. And so that means, once again, we can just drop the boundaries straight down onto our cross section here. Now, you will notice if you look at the labels, the annotations for each of these layers of rock, you have the same layers occurring. So we have HD here, then we have JB, which is occurring there and there. WD occurs here, and YM occurs there and there. So when we see repeating layers of rock, this typically means that one of 2 things has occurred. The first one is the sequence has been folded, and this will result in the same layers of rock appearing again and again due to the folding, the buckling of the strata. The other possibility is that the sequence has been faulted, and in the process of faulting it, you've had packages of rock either pushed over each other or dropped down relative to each other, and this has resulted in this repeating pattern of rocks. Now, when we look at this map, there is no fault clearly labeled. This would instantly suggest that the reason that we see the strata repeating itself is due to folding. So we're going to probably be looking at an anticline or a syncline. So when you look at the map, you are going to see that these 3 beds over here have a dip of 45 degrees towards the east, but do the other dip symbols match them? So another thing that you obviously need to take note is that layer JD is here, and the fact that they are the same layer of rock, and the fact that this likely is the reappearance of the same layer is likely due to folding, means that these layers of rock will connect if they are underground. So if for argument's sake, say this is a syncline, the layer of rock would start over here and it would come under and then it would come back up on the other side. And it would be one continuous layer, all right? And so when you are drawing your cross section, you are going to have to try and make sure that the layers will join with each other underground, assuming it's a syncline. Now, the standard rules also apply that if you have a boundary, so let's say YM and WD, it's coming down at 45 degrees and it hits the bottom of your diagram, it's obviously going to terminate there. All right. So if you imagine there's a possibility that YM and WD, the contact, could come all the way down here, then it could come all the way down there and then come back up on the other side. However, the portion that falls below the bottom of your cross section, you won't draw that. So your boundary will simply come down, it will terminate against the bottom of the cross section here, and then the boundary will reappear and come off the bottom of the cross section up towards the boundary up here. So take your time with this one. Make sure you take note of the dip direction for each of the 6 layers that have dip and strike symbols. Now, once you've completed question 1, question 2 is going to ask you what structure is shown in the figure once you've drawn the cross section. And so you're going to have to work it out. And it's pretty much one of 4 possible options. It's an anticline, it's a syncline, it's a normal fault, it's a reverse fault. So have a look at the structure which you have drawn as part of your cross section and try and work out what kind of structure it is. If you feel uncertain, please refer back to your physical geology notes on folding and faulting. And if you still feel uncertain, please send me an email. Now, for question 3, you are going to be doing pretty much exactly the same thing. So we have another situation where we have repeating layers of rocks. We've got JB again, WD again, and YM again. Once again, this suggests we either have folding or faulting, causing these layers to reappear again and again. So just like you did in the previous diagram, you are going to drop down the boundaries onto the topographic profile below, because once again, our cross section, our topographic profile is orientated east-west, and our line of section is orientated east-west. They are running parallel to each other, so we can just drop this information straight down. So we're going to drop this boundary down, this one, this one, this one, this one, and this one. And then using the dip angle and dip direction shown for each of these boundaries, you are then going to project them into the subsurface. Now, please, for this diagram, take a second and note the dip angles and the dip directions. All right. This diagram tends to be done incorrectly by students because they aren't taking note of the dip angles and the dip direction. So take a second and make sure you know in which direction towards A or A prime each boundary should be dipping. Now, once you've completed your diagram, you're then going to move on to question 4, and that's going to ask you what structure is shown in your cross section. Once again, you have one of 4 real choices: anticline, syncline, normal fault, and reverse fault. Okay. So once you've completed that, you are going to be moving on to question number 5. And this is the diagram for question 5. So question 5 contains a sequence of stratified, so layered rocks over here. And then over here on the right, we have an intrusion, a granite labeled GR. So you'll notice that for the layers of sedimentary rock, you have these nice, relatively linear boundaries, pretty straight. In contrast, the granite has a highly undulating boundary. It's very uneven. And this is because intrusions don't really follow any kind of controlling structure. There's nothing that helps to limit the size of your intrusion short of the amount of magma being intruded. So the intrusion will go pretty much where it wants and where it can. And so this will result in a highly irregular boundary, both in the map view and also when you draw it in your cross section. So you're probably thinking, well, what am I supposed to do then? I'm dealing with a rock unit that has a very irregular boundary, so it's going to be moving all over the place. How am I possibly going to be able to project that boundary, bearing in mind I have no structural data to help me predict where that boundary is going to go? So the first thing about intrusions is, although the boundary is uneven, if you look at the general trend of it, it will typically be quite steep. So most intrusions will have a dip of between 70 and 90 degrees. So their boundaries will be quite steep. They'll be near vertical. And so even though you don't know the exact shape of the boundary itself, it's going to be undulating all over the place, you know what the general trend of that boundary should be. Typically quite steep, between 90 and 70 degrees. So when you project the boundary down here onto your topographic profile, your boundary could be undulating downwards at about 80 degrees in this direction, or it could be undulating downwards, let's say 75 degrees in that direction, or it could just be undulating straight down with a dip of 90 degrees. It's your choice, because I don't know what's happening to that boundary underground. You really don't know either. You're just coming up with a most likely scenario. Now, in terms of the layers of sedimentary rock that you can see over here, the boundaries are clearly crossing your line of section here, 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 and here. So project those down onto the cross section, onto the topographic profile, and then extend them underground. Now, the most important thing to remember is that when a granite intrudes a sequence of sedimentary rocks, the area that is intruded by the granite essentially has its sedimentary layering destroyed. So this means that any of these boundaries that you are projecting underground towards the granite, if the boundary hits the granite, it must terminate against the granite. It must stop there. So remember the principle of cross-cutting relationships. Because the granite is younger, it's pushed through, it's destroyed the layering in the areas that it's moved through, and as such, any layering that you have must terminate against the side of the granite. So your layers of sedimentary rock will not continue through the granite because they've been destroyed. Okay, so that's question 5. So for question 6, we are going to move on to this diagram right here. Now, question 6 is dealing with the intrusion of dikes through a sequence of stratified rocks. So you can see on this diagram, we have two dikes, dy and di. So those are going to be the first thing that you are going to put onto your cross section. So you can see that dy has a dip of 80 degrees, very, very steep, and di has a dip of 70 degrees, also pretty steep. This is perfectly normal for dikes. They tend to cut through sequences of sedimentary rocks at relatively steep angles, so anywhere between vertical, so 90 degrees, and about 70 degrees. So the upper and lower boundaries of the dikes will be 70 degrees and 70 degrees in the case of di, and 80 degrees and 80 degrees in the case of dy. Please note the dip directions for both of these dikes. And so you're going to project the boundaries down onto the cross section below, and then you're going to draw the margins of the two dikes into the cross section. Next, once you have added the dikes, you are then going to move on to the layers of sedimentary rock. And I just want to point out something, which is this right here. Here is layer JD, and you have the same layer of rock right here. So this represents the lower boundary of layer JD, and this represents the upper boundary of the layer JD. Okay, so you can see that JD has a dip of 36 degrees. So the dip angle of this boundary here and this boundary here is going to be somewhere around 36 degrees. Now, another thing you need to note is that the dip angles are not consistent across the map. So we've got 36, 38, 36, 35, 37, and 40. Now, when we have this kind of data, which is more realistic, when we are drawing the dip angle of our boundary as we project it underground, we are going to be using the average between the two adjacent layers. So we can see that this layer LS has a dip of 36 degrees, and this layer here, JU, has a dip of 38 degrees. So we're going to split the difference, and we're going to say that this boundary has a dip of 37 degrees. And once again, please take note of the dip direction, because that's going to tell you the direction in which your layer will be dipping, either towards A prime or towards A. And so you are going to be drawing your boundaries for your layers of sedimentary rock. But the most important thing to remember is the dike is like the intrusion. It's younger, it's pushed through your sequence of sedimentary rock. So anywhere the dike has pushed through, the sedimentary layering has been destroyed. And so this means that your sedimentary boundary will extend underground until it hits your dike, at which point it must terminate. Now, because dikes are relatively thin features, they're not particularly wide, unlike an intrusion, the sedimentary layer will then actually continue on the other side of the dike. So you're going to see your sedimentary boundary coming down, it's going to hit the dike and it's going to disappear. And then on the other side of the dike, the boundary is going to reappear again and continue. In terms of the dikes themselves, dikes tend to have a relatively consistent thickness. So the width of the dike here will be the same width you will use as you project it down into your cross section. Okay, so that's it for question 6. So then we are going to be moving on to question 7. Now, question 7 is quite a lot more complicated than the previous geologic maps that we've looked at. So the first thing is that for question 7, there is this feature which is running down right here. And you can see this has an arrow associated with it with a dip of 80 degrees. This is a fault. All right. So we know that this fault must slice through our sequence of stratified rocks, our sequence of sedimentary layers. So the very first thing that you are going to be drawing in your cross section is going to be the fault, because all of these sedimentary layers must terminate when they hit the fault. So you are going to look at your line of section. You're going to say, right, the fault comes across the line of section right here. I'm going to project that point down to here. And then I am going to draw my fault plane, which is 80 degrees. And you can see the arrow is telling you the dip direction of your fault plane. So it's either going to be towards A or A prime. So you're going to draw your fault first. Then you are going to come over here to the left and you're going to look at these 3 layers of rock, XW, HV, and IG. And you are going to project the boundaries for these 3 layers. And in this case, the dip angle is quite consistent. It's 30 degrees for each of these layers. So you're going to project the boundary down and then you're going to draw your boundary between the layers and you're going to project it into the cross section until it meets the fault. When it meets the fault, it has to stop, has to terminate there. You are then going to repeat the same process over here for this sequence of sedimentary rocks. Please take note of the dip directions and the dip angles. Very important. I would also like to point out over here, we have a change in the dip angle. So this is telling us something about how this layer is changing its dip angle. So we can see over here, this cluster of dip and strike symbols is pointing in one direction, and this cluster, this single symbol over here is pointing in a different direction. This would imply that there may be an antiform or a synform located in this area. So just like on this side of the fault, these boundaries between our rock layers must terminate when they hit the fault plane. They can't go through it. They have to stop when they hit it. So once you've completed your cross section, there's a couple of additional questions that you'll need to answer. So for question 8, it asks you which side of the fault has been down thrown. So which side has gone down relative to the other side. Now, if you've drawn your cross section correctly, it should be quite straightforward to pick out which side has dropped down relative to the other side. In this instance, if you are finding it difficult to work out which side has dropped, it might be a good idea to select a layer of rock and color it in. So let's say layer HV. So maybe in your cross section, you color layer HV in light blue, and there's the same layer of rock over here, HV. So you color that one in light blue, and hopefully that will give you some idea about which side of the fault has dropped down relative to the other side. Now, once you've worked out which side of the fault has dropped down, you're then going to be answering question 9 that's going to ask you what type of fault is shown in the figure. Is it a normal fault? Is it a reverse or thrust fault? Or is it a strike-slip fault? Once again, if you are uncertain, please look back at your physical geology notes. If you still don't feel comfortable answering the question, please email me and I will try and guide you towards the correct answer. Okay, so that's it for the questions for this lab exercise. Thank you for watching the video and have a good day.